So I want to show you how big data creates some new challenges, and methods like dimension reduction, they play a really important role. So there are two methods for let's say dealing with bonds portfolio. A duration method, which is based on Macaulay duration, modified duration, effective duration, basically changing the problem of, for example, you want to find value at risk for a bond portfolio. You're related to value at risk for yield. So that's a different story. But today, I want to talk about cash matching because our clients are banks and they're really interested in cash matching because it is more flexible for them to work with this infrastructure. So cash matching, for example, you have some cash flows. Let's say cash flow 1 at cash flow date 2, cash flow date 3, and here we have some zero coupon bond we have which has a maturity which is different from cash flows. For example, these have different dates, but some of them may match. So zero coupon 2, here it could be zero coupon 3, which is like this one. As you see, some of them really match with the cash flow, but some of them do not match. So this is the problem, that we try to match as much as possible, but if we could not do that, then we should do some kind of interpolation. So the basic idea is like that, because you have, for example, you have a bond which has some face value, and the issuer starts at some dates, and you receive some coupons, you receive some payments regularly, and so you have some cash flows. These are cash flows, okay? You have some cash flows, and you want to match it to some zero coupon discount, because the value of bond price changes. As you know, this is bond, this is yield. This is the value of bond changes. As it changes, so the present value changes. So if you write the bond price as a sigma, so it's a present value. So because the value of the bond changes, the discount factors multiplied by cash flows, these will change. For example, you do it with some bootstrapping algorithm to calculate the zero discount factors. So these are ZDF tables that we need, and there, for example, you can use it as a risk factor. Okay, so we have different methods for VAR, value at risk calculation. One of them historical method, the other one Monte Carlo. And here, for example, is variance covariance approach, which is very common, variance covariance, because it's very simple, and it's very similar to the way you use in Markowitz. And we have full revaluation in delta normal. So historical method, you can use my codes to find that, the Python code. And this historical method simply reorganizes actual historical returns. So it puts them in order from worst to best. It then assumes that history will repeat itself. This is the problem of this method, because history will not repeat itself. So we for example, the other method is variance covariance approach. So we use the weights, and this is the variance covariance. For example, you have some risk factors. You write these risk factors here, and the covariance, variance, and covariance matrix. So it's very general and easy. And for monthly VAR and annual VAR, a simple solution is just multiply by some appropriate numbers. And the structured Monte Carlo, you can find my GitHub. I use geometric Brownian motion, and you can use it for stocks, bonds, any asset classes. So the advantages is that it can generate correlated scenarios based on statistical distribution, and it is flexible. Flexibility makes it most powerful approach to VAR, but it has some disadvantages. The computational time requirement, and because you have some drift term, and volatility, nothing else. So everything is dependent on these two variables. So if your variables are estimated incorrectly, then everything will be wrong. Huang, who wrote an article, very interesting article, he used Kernel Estimator for value at risk. So, historical approach, you can use it my GitHub for historical approach, for Monte Carlo, for variance covariance. And there is another approach which is based on GARCH, Generalized Autoregressive Conditional Heteroscedasticity. And there are other methods like kernel estimation that I just pointed, which is about Huang approach. So basically, it's just using some kernel density functions, and you approximate it with some kernels. And the kernel that we use is typically Gaussian. So this is the Python code for kernel. You just use kernel density, and you say the bandwidth of that. By the way, you can use any bandwidth that you like. H is the bandwidth. And conditional value at risk is subadditive, in contrast to value at risk, which is not subadditive. So CVaR is much more practical, and it is, I say it is expected loss in comparison with VAR, which is just a number dependent on the market value. And we reduce the interesting thing in CVaR, in portfolio management, is that we can reduce the optimization to linear programming instead of quadratic programming. So we solve it using simplex algorithm. So we just reduce it to a linear programming. We don't need to do quadratic programming, and it's computationally it's a big gain. And kernel regression, for example, in CVaR, because you are conditioned on the previous time or previous variable, so this kernel regression is really quite powerful. And so big data challenges in 2020. These are very old methods, starting from factor analysis, very old methods, but still you can see it in finance books. Principal component analysis, very old. But a relatively new one is a kernel principal component analysis for dimension reduction. You basically want to reduce your variables, the number of variables you need to know to estimate something. For example, capital asset management theory, you use it in statistical arbitrage, the different applications. So I want to encourage people to contemplate on why dimension reduction is really important. So we have two principal directions, and so it has basically you find that the directions which has most variation, and PCA for dimension reduction to reduce number of risk factors to a manageable dimension. For example, instead of 80 yields of different maturities as risk factors, we may use only 3 or 4 principal components. And facilitate measurement of portfolio risk, identify the key sources of risk. They may or may not describe economic variables. For example, in principal component analysis, we relate the asset return to some market return. So it has some economic intuition behind that. And the Python code, if you just use the PCA and just you fit it, that's it. You get everything. You get the direction of that principal vectors. So in kernel principal component, like any other kernel method, like support vector machine, they use Kernel Trick. Here we use Kernel Trick, so it's really important. So we just don't use phi of x explicitly, but we use it implicitly. So these mappings are just implicit. So a typical choice, as usual, is Gaussian kernel with h as your bandwidth, and you just need to center the dataset. And after that, you find the eigenvalue problem as it is common in most dimension reduction techniques, and then you project it to a new dimension. And of course, there are many other methods for dimension reduction, especially for nonlinear dimension reduction, Laplacian eigenmaps, and local linear embedding. For example, local linear embedding, you try to find that Laplacian graph as you do in Laplacian eigenmaps, but this one you try to decompose a graph into some patches, and then you find the weights in the x space. For example, you have x space, you have y space. In x space, you find the weights, and then you fix the weights, use it in y, and you do optimization for y. In multidimensional scaling, similar to techniques, variational autoencoders, it's a combination of this one is a combination of deep learning and sampling techniques. So you have a cost function, and so when you minimize it, then but the problem with this is that it is still parametric, and you are just doing. For example, you have 100 normal distributions, 100 parameters you want to calculate. So all the problems that neural networks have, here you have it as well. But there are other methods like independent component analysis, which is not really mature. We have canonical correlation analysis. It is really good if you have two sets of two pairs, and if you have the pair, then you can find you can use this method, and it has some advantages over other methods. Fisher linear discriminant. You understand this method when you get familiar with things like support vector machine and classifiers, and you see how classification could be useful. Ideas from classification could be useful for dimension reduction as well. Linear Dirichlet allocation. I know there is a professor in a university in New York, I don't remember, but he used it for topic modeling and NLP. And the other method is T-distributed stochastic neighbor embedding, the last one. And these are the present, of course, the origin of them are from 2000, some of them even 1964, but the future direction is based on something like sufficient dimension reduction. Methods such as non-negative matrix factorization And you can develop hundreds of methods. Just sufficient dimension reduction. Sufficient comes from sufficient statistics, which says, for example, these methods are good for regression-based dimension reduction, and let's say you say y dependent on x, the distribution of that. You have basically the sufficient statistics. You have the same sufficient statistics if you condition an x, or you condition of the reduced space. You have you don't lose any information if you condition on a space or a reduced space. So basically this is the idea. And finally, you need to do some backtesting as you do in algorithmic trading, in the portfolio optimization, portfolio selection, and stress testing, and after that, scenario analysis. So backtesting, as you see, is a process of comparing losses predicted by the value at risk model to those actually experienced over the sampling testing period. For example, what happens if you have corona, and stress testing during times of crisis, financial crisis, and finally scenario analysis. Analyze different predetermined stress scenarios, such as and it has some advantages. It is not limited to evaluation of risks. The disadvantage is that the risk measure can be deceptive, and you try to use the worst case scenario. Assume that an unfavorable event will occur with certainty. The focus is on distribution of worst possible outcomes given an unfavorable event.